Okay. Good afternoon, everybody. I hope everyone's having a wonderful day. So today I'm going to be picking up from where I was last day. Now, last day I introduced you to the subset construction, but also a so-called lazy version of it, which allowed us to only construct the reachable or accessible states from the start state. So it made a lot less work for us when we did it that way. What I'm going to do next is I'm going to prove an important part of the overall scheme of showing the equivalency between NFAs and DFAs, is proving that that subset construction indeed works. So I have to show you that subset construction is indeed correct. So it's going to do what we said it's going to do. It's going to take an NFA and it's going to create from that description a DFA. And that DFA is going to have to be able to accept the exact same language. That's what the statement of this theorem, or lemma, because we're going to use it, states. It's going to do most of the heavy lifting for the big part of this proof. So I'm going to get started. I'm going to make some important observation. And once I have that, I'll have the building blocks to make a proof for us. And this proof is going to use mathematical induction, because the way we define the computation of a DFA or an NFA is using induction. So since we define it inductively, it makes sense to use induction to prove that these two things actually do the same thing in quotation marks. I don't want to spoil it too much. So I'm just going to say, I'm going to let W, it's going to be just some string of sigma star. Now, this is going to be the big observation for this proof, is I'm going to observe that both D and N accept if and only if, I'm going to use IFF to abbreviate if and only if. So whatever I say here is going to be logically equivalent to what I'm going to say next. If and only if both a delta hat for the NFA, I'll call it delta hat N of Q0W, and delta hat D, this is the extended transition function of the DFA, the extended transition function delta D, Q0, given, remember this is the label for a state, W, contain a state in set of final states of N. So remember, in the DFA, we have a whole bunch of labels for a whole bunch of subsets, right? All the subsets of my NFA, right? What I'm going to do is I'm going to use this idea so that I know if this is in fact going to be accepting, this has to also accept. That's going to be the idea with our proof. So I'm going to use induction to show that in fact these are going to be equal to one another. So the sort of the spoiler with this is if you look quite closely, it's like, okay, well, this one looks a lot like that one, but that one has curly braces around it. It's kind of interesting like that. That idea is going to come up a little later. So I'm going to give us a game plan of what we're going to do. We prove via mathematical induction on the length of W that delta hat of D given state Q0 with the curly braces, so the set containing Q0 W, is equal to delta hat N of Q0 W. So we're going to prove this using mathematical induction. We're going to perform induction on the length of the string W. So I understand the game plan. So I'm just going to show that whatever's over here is going to be also over here. But remember, keep in mind that we're going to be talking about, in one case, labels that are going to correspond to sets of states. The other one's literally a set of states. So we're going to interpret them in that way. So that little thing, otherwise, if you don't get that, it gets a little confusing at one part in this proof. Okay. So if that's the case, let me proceed. So when we use mathematical induction, there's kind of two big parts, right? So in the principle of mathematical induction, we have a base step, which we'll call the basis, because I just like to be consistent with what I've been doing already. And then there's this induction or inductive step, which I'll refer to as the induction step. The idea is that I need to prove a statement for the base step for the smallest possible value for which the statement is going to be true. And then for the induction, I need to, of course, show, assuming some fixed value that's going to be, of course, at least the base step, that if I go from one rung on hypothetically a ladder, which is going to represent the statement for some arbitrary length n, I want to show that logically it follows that the next rung, which would be the string with one extra symbol, the statement's also true. So the analogy I like to use is that I use it's like teaching a cat how to climb a ladder. Let me just go grab one. I need to go grab a cat to make this a little easier to explain. Come here. I need one of you. I need one of you. Okay. Come here. I don't do enough props in this class, so I need another fun prop. So this is Miss Kitty. Everybody say hi to Miss Kitty. So when I do mathematical induction, it's just mostly a reminder of how mathematical induction works. So I start off with a base step. So imagine I want to teach Miss Kitty how to climb up a ladder to a bunk bed so she can sleep in the bunk bed. So what I do is I teach Miss Kitty how to go up the first rung with a base step. And then I got to assume Miss Kitty's at an arbitrary rung of the ladder, say up here. She's very wiggly. What I have to do is I have to show Miss Kitty how to climb up any arbitrary ladder so the cat can get up the bunk bed. So I can teach the cat how to go from one rung to the next, to the next, to the next. The way I do this is by showing that on an arbitrary rung, that from that arbitrary rung, I can get to the next rung. So that's going to be the idea in our proof. We're going to use this idea, this inductive hypothesis. and we're going to do that. And Miss Kitty, thank you for your help. I really appreciate it. I know you're having a nap, so let me let you go. Don't worry. Miss Kitty really enjoys it when I do this kind of stuff. She's a bit grumpy at the moment. She just had a nap. I promise no animals have been harmed in the matter of this demonstration, I assure you. But yeah, no, Miss Kitty, she loves wiggling around and all that stuff. Anyways, does everybody understand the idea? So I need to prove for any length of the string, this is true. And I'm going to start off with a base step, and then I'm going to work from any arbitrary step to show you that it logically follows that the next step can be demonstrated. Okay, so I'm going to start off with our base step. I'm just going to refer to it as a basis just because I've been doing that already. So I'm going to consider when the length of the string is 0, because that's the smallest value it can take on. Namely, it's the empty string, right? That's when W has no length, right? So W equals the empty string by the basis of delta hat of D, delta hat D, where I get Q0, the state Q0 with the curly braces, of epsilon, and delta hat of N, Q0 epsilon. Both of these, when I feed you no symbols to it, what happens? It just stays in the same state, right? So when I have both of these, and I have Q0 here, and I have Q0 here, what happens? Both of them are going to be, both are Q0, right? In a set, like this. Right? So in the DFA, remember, this is a label. We're going to interpret it as a set of states in the NFA. But when I don't read any symbols, it has to stay in this state, right? Likewise over here, I don't read a symbol. It's Q0. It has to return a set of states. And since it didn't move to any other state, it must be in Q0 still. Does everybody understand the base step? Hopefully I'm making this buttery smooth. Maybe not as buttery smooth as my writing, but it's definitely buttery smooth, hopefully. So if that's the case, I'm going to proceed to the induction step. So let me do that. So this is where we're going to start pulling out definitions from the transition functions. Because it's going to, so both delta, the extended transition function, because remember that's part of what we're trying to prove, and also the transition function. So I want you to try to remember what those looked like when we did this. So we're going to consider the induction step. So this is going to be where I'm going to presume that I'm given some n for the length, and I'm going to go one higher. So I'm going to fix some n greater or equal to 0. Then let the length of the string equal n plus 1, assuming the statement is, of course, my equality right over there that we had over there before. Assuming the statement for when the length of the string is equal to n holds. So this is going to be what we call our induction hypothesis or inductive hypothesis. I'm going to abbreviate it as IH. We're going to invoke it at some point. Because our things are all defined inductively, you're going to find that using induction like this is going to feel very natural after you see it a couple of times. So now I'm going to use the same idea I did when I defined the extended transition function. I'm going to split the string up so I have everything to the left of the last symbol and then just the last symbol. So consider W equals XA, where A is the last symbol of W. So now here's where I wouldn't call it magic. It's not really magic at all. It's just mathematical induction. By the induction hypothesis, by IH, by the induction hypothesis, what can I say? Well, I'm going to consider it for length n. But what's a string of length n if you think about W when it's decomposed like this? Can somebody point? So which one of these two is a string of length n? Is it X or A? So is it X or A? One of these is of length n. Which of these two? Yeah, X. Yeah, X. So we're going to invoke the induction hypothesis on X. This is where the beauty of mathematical induction is going to start kicking in, okay? So I'm hoping by doing this a little bit more carefully, you're going to appreciate this. It's one of these neat little structural aspects of these machines. So delta hat D, given Q0, it's X is going to be equal to delta hat N of Q0X. So what I'm going to do after this is I'm going to let there be a set. I'm going to denote it as P1, P2, Pk be the sets of states of n for both these sets. So all I'm saying is, okay, I want to know what I'm going to name all these sets. Sorry, I want to name all of these. So I want to know what these are. I'm just going to give them a name. P1, P2, Pk. So these are all going to be the set of states that are going to be, in this case, representing labels. And in this case, are going to represent literal states, as like a set of states. Does everybody understand? Are we all good? So the reason I'm going to write this is it should look eerily similar to what we did with the NFA. Just watch this. Well, by the inductive part of the definition of the extended transition function for a NFA. What was the original definition? Let me write it down for you. Well, it's the delta hat for n, given q0 and w, is, remember, if I give you, so you got to think of it like, remember what we did when we had the extended transition function for NFAs? I imagine I have a set of states that currently it is after processing x. What's going to happen is, remember, when I read the next symbol, it's supposed to tell me all the states that you can transition to on symbol A from all of those states, right? So that's all I'm going to write here. So this is the union from I is equal to 1 to k of delta n I A. So this is just me invoking a definition. So I'm going to give this a name. I'm going to call it star. I'm going to call that star. Now, there's a lovely property that the subset construction actually has. So in addition, a property of the subset construction is that, now let me write it out. So remember, the set of states is now a label when I talk about the DFA, but delta D of P1, P2, all the way up to Pk, given A, symbol A, is of course the union. Remember what we did with the subset construction? If I give you a bunch of states and then you give me a symbol A, what I do is I look at the transition function of the NFA and I look at all the set of states I can go to, all the ones I can touch on from moving on transitions on that symbol. Then I take all those and lump them together into a set, right? That's what I'm just describing here. So I'm going to call this, I'm going to put 2 stars beside this one. So does everybody see these 2 properties, why they're true? So I'm making these 2 observations here. So I'm going to piece them and stitch them together to get us our result. So this is going to be pretty neat. Okay, so let's get to the fun part of this. Although I think all of it's pretty neat. So just remember, we're going to be using parts about the NFA and parts about the way we construct the DFA from the subset construction. This is no different than, say if we want to think about this in terms of algorithm design, this is no different than what you would do when you're designing an algorithm to solve a problem. When, in that sense, what you do is you identify properties that a problem has, you prove the problem has that property, and then you design the algorithm to do that. Here we're literally having it where, okay, I'm given an NFA, I'm going to use properties of the NFA to show that the subset construction is in fact going to get me a DFA that matches the same language. So I use properties of the NFA and the properties of the process I use to build the DFA to show this. So the mindset is not that much different. I just like to make sure that I'm trying to stitch this idea together. So since delta hat D, given the state, the set Q0, X is equal to the set P1 all the way up to Pk, all we're going to do is we're going to use the inductive part of the definition for the transition on a DFA. Applying the inductive part of the definition of a DFA, DFA's delta hat. Now I can write this like this. This is going to be really slick. So watch this. So I'm going to imagine I give you the entire string W. I give it to the DFA D. So what I'm going to do is I'm going to use the definition of the extended transition function like we did before, like I think there's at least a couple lectures ago. So I'm going to use that. Now, does anybody remember the definition roughly of what we did with the DFA for a transition? So for the delta hat, we had it where we did something right here involving the transition function, right? So just to, yeah, so it has, yeah, so you'll have your part with X right here first, right? Am I right? So you're going to process something involving X first, and then you have the symbol A, right? It kind of like wraps it out. It pushes out one of the symbols. So you have the extended transition function, the D, like this. And of course, remember I have the part about X. So remember we did this before. It was a while ago. Just there's more symbols I'm using to represent things. So what's the part I write here again? So imagine I have the last symbol. What is the last symbol called? A. It's A, exactly. So now, well, what's this? What's this? What's this? It's up there, right? It's P1 all the way up to Pk, right? So delta D of P1 all the way up to Pk, given symbol A. But what is this? What is this? This looks rather interesting. Well, we derived something that's actually kind of interesting before, right? We had something over here that kind of told us something to do with this. What was that? Let me just scroll over here. So now I have something that states something about like a label that represents this set of states, and I have an A here. Can somebody tell me, there's something over on this board that looks like eerily like that I can use directly? So I gave them names. Which one? Yeah, so there's star here and then there's double star. But notice this one is the one involving delta D. So we can use this because that was a property of the subset construction. So we're going to use double star. So we can use double star now. We're going to use that. So I'm just going to invoke that. So what does that mean? It just simply means that this is equal to the union from I is equal to 1 to K of delta N PIA. So this is by double star. That's by double star. So now this is the great part. This we've done all the work we really need to do, because what is this? What's that? That's the union of all of the like I take the transition on the NFA over all the symbols, touching all the states using symbol A. But what is that? That's what I established over there before, right? That's delta hat for the NFA, right? So it's delta hat n q0w. This is by star. Boom. Is that nice? So now we have established that these are in fact equal. But notice how I did it. I used the induction hypothesis, and by using that, I can show you how I can extend it by one symbol. And that's really relying on how I use the extended transition function on the DFA. So I could say thus completing the induction step. It's sort of melted in the microwave, but it says thus completing the induction step. So now I can invoke the principle of mathematical induction because I have a base step and an induction step laid out. I can say therefore by the principle of mathematical induction for all strings of length 0 or greater, delta hat D, where the state that it was representing the set Q0, W is equal to delta hat N. That's what that delta looks a little sad. I'm gonna fix that. There we go. N of Q0 W. And what does that mean? What does that mean, everybody? And as a result, what can I say about the languages that both machines recognize? They're the same. They're the same. Exactly. The chat and the voice got everything, right? This is perfect. As a result, L of D is equal to L of N. And we're done. Boom. Proven. We did it. So hopefully the steps I've explained to you really help make this look actually a lot less intimidating than it might look otherwise. Does everybody understand this proof? I consider it a nice classic. So it's important that you're aware of just generally how we applied induction here, because you'll find that very often when we start talking about more machines, we'll start trying to use this idea of induction to try to find properties between two different types of models of computation and see if there's any relationship, like this one. So we had a process to build another machine from another description. We're going to find that we're going to be able to do this several times throughout this course. And this is actually quite a powerful idea if you think about it. I was able to take something that at first I told you had all these capabilities, but actually there's a way of transforming it into something that looks a lot more down to earth, even though both technically have their own descriptions. You could describe them to somebody, you could put them on a computer. It's just this DFA business, that's what connects us to the regular languages, right? So that's all I have to say about that. So now I want to prove the big theorem. So I'm not going to go into all the details of this proof. I have the full proof in the notes. I'm just going to give you the idea of the proof, because we've essentially done kind of like the heart of the proof. The heart of the proof is the subset construction. Subset construction is probably is what I would consider the non-trivial part of this entire theorem. So here's a theorem that says theorem. A language L is recognized by a DFA if and only if L is recognized by a NFA. So that's the big theorem. So whenever I give you a language, if this language is recognized by either a DFA or an NFA, there is some way that I'll know for certain it's regular. Well, if it's a DFA, it's regular right off the hoop. But this if and only if connection allows me to go between an NFA to a DFA and a DFA back to an NFA. This is essentially the powerful idea I've really been trying to prime you to up to this stage. So I'm just going to give you a proof sketch. You can read the full proof in the notes. So I'm going to give you a sketch for this. So I'm going to consider each part of this. So first, imagine I want to show you that if L is recognized by a DFA, then L is recognized by a DFA. So I'm going to use arrows to indicate this. So you want to imagine that I'm considering if L is recognized by a DFA, then a language is recognized by a DFA. I'm just imagining like I have this laid out in a row, and I'm just saying prove this direction. And then I'm going to prove the other direction because it's an if and only if claim. So, because this is a rather sophisticated claim. It's not just like, oh, this is equal to that thing. It's a little bit more complicated. So you have to be more careful. So you have to prove both directions here. So this direction, so proving the NFA to a DFA part, we already did. This follows from the lemma, i.e. the subset construction. I described to you like I said, it does a lot of the heavy lifting for me. So I described to you how you take an NFA and make a DFA. And we proved that that process is in fact correct. Now the other direction, this is the one I was going to say, oh, it kind of feels like cheating. But watch this. I can prove, so I could construct. So remember I told you that if you think of determinism and non-determinism, determinism is a special case of non-determinism. So what I should be able to do is effectively wrap, if you're familiar with the concept of a wrapper, not like yo-yo kind of wrapper, I mean like a wrapper like in software, where you abstract one by wrapping it, like a class, for example, inside of another one. I'm going to effectively use that idea here. I'm going to say, okay, here's the description of a DFA. Now I'm just going to wrap it in the language of an NFA, and that's all I'm going to do. And it's literally going to look like I'm going to wrap something up. So it's going to feel very like it's going to look like I'm cheating, but it's not. It's really that simple. So to prove this direction, so I'm going to be showing that if a language L is recognized by a DFA, that L is recognized by an NFA. So what do? Construct NFA N from a DFA, D equals Q sigma delta D Q0 F, same parameters as usual, where N is going to be equal to Q sigma delta N Q0 and F. And all I'm going to do is the following, because I notice that everything about this is exactly the same except for one thing. So notice I have Q sigma is over there, Q0 is there, F is there, delta N is going to be different from delta D. I'm just going to do one very simple step. As I said, I'm just going to take the description of the DFA, I'm going to wrap it in the language of an NFA, and then boom, I have an NFA. So watch this. It's gonna. So, and if delta D QA equals P, then I'm going to say that delta N Q0A, that should be just QA, then delta N QA is equal to the set containing P. So this is what I mean by wrapping. So not yo-yo, I'm meaning literally like you take what you have, you just wrap around it a set. So whenever you have a transition in the DFA, all you're going to do is you're going to put curly braces around what that should be for the NFA. Because remember, The NFA returns a set of states as opposed to just one state. And that's all you have to do, believe it or not. And the proof for this uses mathematical induction. So it just uses principle of mathematical induction. The proof is in the notes. So does everybody get the gist of the idea? So one direction I use subset construction, the other direction I build a NFA from a DFA. And all I do is I just simply just make it so instead of returning just a state, it returns a set with a state in it. Because you agree with me that, okay, well, every DFA, if you think about it as an NFA, it should just return exactly one state. That's it. Does everybody understand the idea here? So this is essentially the sketch of the proof. Is there any questions about this? Are we all good? Don't be shy. Because if they were all good, I'm going to move on to something else that's going to be a bit different. I think we're good. I think we're good. Let me just figure out where I'm at here. Ba-ba-dum-ba-dum. Ah, here we are. Okay. I'm just trying to find my notes because I was getting really excited earlier. Let's see here. Induction. By the way, did you take a look at all of the examples with the subset construction I provided in the notes? I thought they might be helpful, so I think included some extra examples. Let's see here. Where is that? No, well, let's just proceed this way. Okay. So what I'm going to do is I want to entertain you with another model. So I've talked about NFAs and DFAs. I'm going to consider a variant of an NFA that gives me more, what would be perceived as more computing power, but it really doesn't. But I don't want to spoil it quite yet. So what we're going to do is we're going to consider what can happen if we just introduce another feature into our NFA. And you might ask, Dan, why would we do this? It's because it makes it a little easier to design the NFA if we introduce another feature to it. And I'll try to motivate it, and that should basically be the rest of today. So let me just proceed. So we're going to consider NFA with so-called epsilon transitions. Epsilon transitions, which I'll abbreviate as an epsilon-NFA. Yeah, so that's an epsilon-NFA at the top there. Wrote a little too high there. So what we're going to do is I'm going to take the idea of an NFA. Now remember, on an NFA, we can go to a set of states, right? So here's the idea. Allow the NFA to transition on the empty string. Epsilon. So that's going to be the fundamental difference that's going to happen. Is I'm going to allow the NFA to have transitions that consist of epsilon. Now, you might say, Dan, okay, that's something, but what does that mean? But what does that mean? Actually, I want to ask you, do you have any ideas what this could potentially do? Like, do you have any ideas what this could potentially do to the NFA if we allow this to happen? Any suggestions? Yeah, so that's one idea. That's one idea. That's pretty close to what I'm thinking. I'm thinking of something even simpler than just that. Just simpler than that, even simpler. So remember, when we did the NFA, we did transitions on, so I transitioned from a set of states to another set of states, but I did it by moving along, like I look at the transition on that symbol. But what is epsilon? Epsilon is a string with no symbols in it, right? But what does that mean? What does that mean? What can happen when I do my transitions? Do I have to even read a symbol? Yes or no? No, right? I don't have to read a symbol anymore. I could get spontaneous ability to move from a state to another state, which is very interesting if you think about it. So transitioning on epsilon, which sometimes people call this an epsilon move, means spontaneously, means right away, like without any hesitation or anything, means spontaneously transitioning with no input symbol. So I want to motivate this by giving you a couple of examples of why you might consider a machine like this, because like just also give you a flavor for how this is going to work, because I'm going to have to formally define what an epsilon-NFA is for you. I'm going to give you kind of two applications of sorts, just to kind of motivate this. So remember last time, or I think it was last time, or if not, it was the time before that, we talked about how you could use an NFA to detect words that are consistent or contained inside of a string, right? Like we had the cat-tack example. Now, I want you to hypothetically imagine that somebody was typing on a keyboard, and you want to make it so that as soon as it recognizes that you've typed in a sequence of string, so on my string, I want to see if, oh yeah, no, this person all of a sudden has typed in a keyword, and I want some action to happen. I would like to be able to design a program or a machine, whatever way you would like to think about it, that tells me, yes, that is a keyword, and you should accept. So I'm going to think about it instead of detecting keywords in this way. So I could design an epsilon-NFA like this, and you're going to see. So I'm going to suppose that I have an alphabet, A, B, all the way up to Z. So all the lowercase English letters. So all of these guys. So I'm going to design an epsilon-NFA that's going to recognize certain key words. So I'm going to label the initial state 0. I'm going to have a loop, because I don't feel like writing out all of them at once, like A, B, C, D all the way. I'm just going to write sigma, because that's the alphabet. That's a list of all of them, if you think about it like that. And then what I'm going to do is I'm going to make two paths here. Now, I want you just to think back to the other day, what I did when I wanted to detect a key word. Now, remember, there I did something a little bit more involved, where I just looked if it contained a word. Here, I just care about if the word is just the last thing that the string has processed. So I'm just going to make a couple of paths here. Call this one pan. That's supposed to be a final state. And I'm going to have another one. I'm going to label it no. Actually, let's make it more fun. I'm going to make this Pam. Pam, no. Pam, no. So what I'm going to, so now this is where the power of the NFA comes in. Now, I showed you a strategy for doing something like this with an NFA, where what you would do is you would put the first symbol on this arc, and then you'd lead that way, right? Well, with an epsilon NFA, you could do something even simpler. So instead, I could just put epsilon right here on both of these transitions. And then I could say, okay, well, I could keep taking in and processing the string over here in state 0. And what happens is, if at any chance, I'm more than welcome to spontaneously go to either state 1 or state 5 at the same time. I'm welcome to do this. And I could transition immediately over here. Why? Because there's no symbols, right? Does everybody get the idea? So notice, instead of having to transition on a symbol, now I could just get for free all of a sudden right here, and I could literally design my keywords like if they're literally paths. I don't have to do anything fancy-pantsy. Actually, I forgot a final state right there. Let's put that there. So this epsilon NFA, for example, will help you detect keywords Pam and no. Does everybody understand the idea? So notice that when I use epsilon here, it spontaneously will allow me to go to state 1 or state 5. And at the same time, I could stay in Q0 because, in state 0 because I have a loop here. So I essentially could stay in 0, 1, and 5 at all times. Because every time I could just spawn immediately 2 threads, hypothetically speaking, to get me into 1 and 5. Does everybody understand that? So this is just a way you could design this much simpler than I did before. So the epsilons allow me to do things like this. I'm going to do one quick more example, and then next day we'll come back to doing some more stuff with epsilon NFAs. So let me just do one more example. This one's a classic, so I had no choice but to show it to you. Somebody in the chat's getting very clever here. There is going to be something like that that's going to be happening. We're going to see that next time. I was going to be showing it today, but I decided instead I was going to show you this proof because I consider it a very important one to see. But yes, the answer is yes. There is going to be some way to transform these machines. And believe it or not, you have most of the mathematical tools to do so, but we'll see next time how to do it. So let me just do this one last example here. Yeah, because I was hoping to do it today, but ends up the proof I thought was a little bit more important. So I'm going to consider the example of reading decimals. So this is a classic. So what I want to do is I'm going to design an epsilon NFA that accepts strings of the following format. One, takes it an optional plus or minus sign, then a string of digits, then it's going to take in a decimal point, and finally it could take in another string of digits. Now here's the catch. Here's the catch I'm going to throw in here to just make it a fun wrench to throw in here. I'm going to want to have it so that it's either this way or that way, as in that it must be either one. So one of these two must be held. That is that one of these two has to have at least one digit. So for example, I'm allowed to have it so that it could proceed immediately to having so if I want to have plus, dot, and then have a bunch of zeros and have like a 5 or something, I'm allowed to do that. However, if I want to have, say, for example, like negative 0.1, I want to have it so that at least one of these two sides has at least one symbol in it. So that's the catch. So I'm going to show you an epsilon NFA, and this will be the perfect place for me to stop. So I'm going to design an epsilon NFA as follows. So I'm going to just have my start state being Q0. Now this is how I'm going to use the epsilon transition. Notice, remember, I said it's an optional plus or minus sign. So I'm going to allow an epsilon transition plus and minus to be transitions on Q0 to get me to Q1. So this is how I could control if it's optional or not. I could use an epsilon transition. So that saves me a little bit of time when I'm designing things. So However, now there's some choices I can have here. I'm going to allow it to stay in Q1 if you want to read in some 0, 1, all the way up to 9, some digits. So some numeric digits. Then I'm going to allow it either to transition to a dot, a period, or decimal point. Or it could transition to reading a digit. Now you might ask, Dan, why do I need this right here? It's because I'm going to have two options, right? I'm either going to be able to enter in as many digits as I like, or I can immediately proceed to the dot, or I want to make sure I could read in at least one symbol. And in this possibility, I want to make sure that at least this is to satisfy this condition, that at least one of these two has one digit in it. So watch this, watch this. So Q2, Q4. And I'm going to introduce a Q3 here. So the purpose of this one right here is to ensure I have at least one digit on the right side of the decimal. So there's going to be kind of two cases you could think of it. There's going to be one case where I have at least one digit on the left side of the decimal point. Then I'm going to have another case where there's at least one digit on the right side of the decimal point. So naturally, I'm going to have a dot on this side. And then I'm going to allow you to enter in as many digits as you like of 0 and 9. But this is the trick. I'm going to use an epsilon transition right here. This is to ensure if I don't want to enter any digits in, I could go immediately to the final state right here. So looking at this, you can see that the two cases are indeed satisfied. So if you look at this, so first I have my optional plus minus. There's two cases. There's a possibility I'm going to enter in some digits. So if I take this path, I could guarantee there's at least one symbol on the left side. Then I could take the decimal point. Or if I want to take more, I could indeed stay here in this state and read more, or I could transition on both of these if I'd like. Remember, this is an NFA still, right? And then I could read, this guarantees me at least one symbol on the right side of the decimal point if I decide to immediately transition over here from a dot. So notice that this will allow me on the right side put as many in, but we have an epsilon transition that lets me get right to the final state if I don't want to enter any more in. So the way I like to think of the epsilon transitions when used in this way, you can think of it like optional input. So imagine you have it in your specifications that, oh, you can maybe put this in. I like to also think of it almost like if you had a user that has the option to type more in. This is essentially one feature you could use to do that, is that you have an epsilon transition that effectively allows it so that if the user enters in more stuff as input, you could effectively have it so that this will make sure that that extra stuff doesn't matter. But yeah, there's a couple ways you can interpret this, but I just wanted to give you a flavor for what epsilon-NFAs are going to be about. So next time, when we come back, we'll talk more about epsilon-NFAs, and I'll show you how epsilons and NFAs relate to DFAs. So I'll say thank you very much, and have yourself a beautiful day. I'll see you later.